Hello everybody, Josh Paul here, back again to explain some of the key topics that you guys will need to understand for your exam 3 for Chemistry 232. So here on the board are just a couple of the reactions that are very important for some synthesis reactions that you guys will be partaking during the exam. So during the exam, you're going to be focusing a lot on not just manipulating with one reaction, but you're going to be combining multiple reactions together from concepts that you've learned, such as substitution, addition, elimination, and now synthesis of alcohols and reduction of different other compounds. So it's very important that, for one, you make sure that you familiarize yourself with all these reactions that you have up here, and you're able to predict the product of what you're gonna get from based on the starting material. Because now, instead of just having this starting material reacting with this to get you your final product, they're gonna be combining 3 or 4 of these types of reactions together and forcing you to think critically about the stepwise process that's going to take place and how you get from this to a more complex molecule such as this. An example is actually over here. This is one of the test questions, or an example of a test question that you might see. Starting from a very complex molecule like this and understanding that you're not just having this reacting with one thing to get you some new material. You're having substitution, or in this case, you're having elimination, and then you're having proteination, and then you're having oxidation to get you your carboxylic acid and your carbon dioxide gas. So at this point, I want you guys to pause this video and write down all of these mechanisms or all of these reactions on a separate sheet of paper or a flashcard. I recommend using a flashcard because you have to memorize these reactions. The only way you'll be able to do well on this next exam is if you know specifically what your product is going to be if they give you a reaction like this. So the best way to study for this is to have a set of flashcards. You can go to Walgreens, grab like 180 flashcards, and just write each reaction that you see on this board on the flashcard. You can have starting material and then this on the front, the reagents and starting material on the front, and then predict the product on the back. And then you can switch it up as well and have your starting material and your predict the product on the front, and then force yourself to remember what the reagent is gonna be. So at this point, please pause and make sure that you write every last reaction on the board down, because if you don't, these reactions will almost be guaranteed to show up on your exam in one way or another. So at this point, go ahead, write these reactions down, and then try to understand what the common theme is, such as understanding that if you react an aldehyde with NaBH4, you produce an alcohol, but noticing that if you react NaBH4 with the carboxylic acid, you get no reaction, versus if you react a carboxylic acid with LAH, you get an alcohol, and if you react an aldehyde with LAH, you also get an alcohol, knowing that LAH is therefore a harsher oxidizing agent than, or harsher reducing agent than NaBH4. So please make sure that you understand this, because as I start to explain the synthesis and the arrow pushing mechanism behind these reactions, it's going to be very important that you're able to deduce how to get from one starting material to the final product. All right, guys, so welcome back. Now I'm going to explain some of the things that you will be seeing on your next exam. So a lot of stuff that deals with alcohols, the mechanisms aren't as crucial. A lot of the mechanisms you're going to be seeing on the test are going to be dealing with alkenes and alkynes. And that's just because those mechanisms are actually simpler and longer. Like if we were to look at one of the mechanisms for LAH, that would require, that's one of those mechanisms that's like 10, 15 steps. So you're not at that level yet, but for Orgo 2, you'll definitely need to understand those mechanisms. But for now, for the most part, dealing with alcohols, you guys just need to know how to predict the product, and then also understand what reagents do what, and why we're using certain reagents. So the nice thing about alcohols, the reason why I actually like the alcohol section a lot is because you are literally producing an OH. So that simplifies the work that you have to do a lot more, because you know, if you go back to rewind a couple minutes ago, you know all those reactions produce an OH, so that limits you to only a subset of reactions that you have to focus on if you have to do a reaction that involves producing an alcohol. So in this case, this is this is a type of question that you may see, right? So what do we see here? We see that we're going from propylene, which is this molecule here. We're going from an alkene and we're creating a carboxylic acid. Now, at first glance, this might seem like a very complex reaction. You're going to be thinking to yourself, how did we go from this to that? That's just, and when you first look at some of these other reactions, especially the ones down here, I don't want you to get scared or get stressed out about we are going from one molecule to a completely whole new molecule. Break it down and determine what changed. What is different in this that's different from the starting material? So logically, we know that we are getting a carboxylic acid, right? And we know, based on what we've done with alcohols, the way to get a carboxylic acid that you guys have learned so far is to go from an alcohol to a carboxylic acid, which means before we get to the carboxylic acid part, we must first get an alcohol. So that logic that I just used is the logic that I want you guys to try to use when you're answering questions like this. It's a stepwise process, right? You can't just go straight to a carboxylic acid. I mean, you could, but you wouldn't get this same starting material. Therefore, you know, in order to get this, you most likely need to start off with an alcohol. And if you need to go from an alkene to an alcohol, we know there are two ways to do this. Either you can use H3O+, or you can use BH3, THF, peroxide, and sodium hydroxide. So in this case, let's look at what happens when we use BHF and peroxide. We know that this gives us the anti-Markovnikov product. So instead of our OH being placed on our most substituted carbon, which would be this secondary carbon right here, we know our OH is going to be placed here, right? Because our OH is going to be here, now we know that we have the alcohol, and then we can convert this into a carboxylic acid. And I don't want you guys to get confused with taking this and going here using LAH. Remember, LAH is a reducing agent. So LAH does the reverse process. If we wanted to go from here to here, then we would have to use LAH, because now we're removing oxygens, we're reducing, right? But here we're kind of adding oxygens, therefore we're oxidizing. So oxidizing agents are going to be your K2CR2O7 or your Na2CR2O7. They're both synonymous. So we know that in order to get from this to this, we must first start off with an alcohol using BH3THF. And we know that since our carboxylic acid is on our least substituted carbon, we have to use BH3 instead of H3O+, because H3O+ would have given us our alcohol on this secondary carbon right here, right? So that's the reasoning behind this product formation here. Moving down to the next one, we see that we're also starting off with the alkene again, but instead we're adding both an OH and a Br, right? So think about this. Anytime you have an alkene like this, the most probable reagent you're going to use to get an alcohol will typically be MCPBA. These are one of these little hints, one of these little shortcuts that as you do more problems, you'll start to realize that there's a general pattern. So we know if we use MCPBA, we're gonna get this molecule. Let me draw this better. We're gonna get the epoxide, right? Like this, without the plus. With our methyl group there, right? And then we know that if we're gonna add our Br on our more substituted side, we know that we have to do this mechanism via SN1, because HBr is an acidic molecule. So then if we use acidic molecules, we then allow, or we then induce the epoxide opening to occur via an SN1 mechanism. The reason why that's important is because what happens in SN1, this is why you cannot, I can't stress enough, you cannot forget the material that you have learned before, because everything is connected and everything pieces together. SN1 occurs via an intermediate, which means you form a carbocation. If you're forming a carbocation, remember the stability is tertiary, secondary, primary. Therefore, this is a tertiary carbon here. So we want our positive charge to be on that, to be on the tertiary carbon rather than the secondary carbon. So in this case, actually, the OH should actually be on this side with the methyl group there. I left out the methyl by accident. So here we see that this should be plus. If we open this, this should be plus right there. And then the OH will go here, allowing the Br to then come in and attack right there. Because remember, the H is going to be taken away by the lone electrons on the oxygen. The oxygen is going to essentially attack this H and push these electrons on the bromine, allowing the bromine to become Br minus, and then the minus then attacks the positive carbocation that forms when the epoxide is opened. Because remember, once the epoxide is opened, that means that this OH is now going to go over here, and then that bond is going to get broken. Right? So that's one mechanism that's important to understand. Going down to more complex reactions like this, it's very easy to get overwhelmed when you see something like this, but figure out what's going on. You're doing a simple elimination reaction here. You start off with 2 bromines, and now you have to eliminate both of those bromines to form the alkyne. The easiest way to do that is with NaH, Na, NH2, and H3O+. And it's as simple as that. And then you know that if you do that, you're going to also form a carboanion. Right, because this product gives you 1, 2, 3, like this, like that. So then you know you need a proton source from H3O+ to then protonate it so that now this becomes the terminal alkyne, like this. So that's just, this is a simpler way of doing this. And you don't require as much thinking, but if you get overwhelmed by seeing the drastic change in the molecule, you can stress yourself out and forget the actual process. Another example here is working with the production of 2 alcohols. Kind of like the same thing we did up here, but remember how we said LAH has an opposite effect of K2Cr2O7? Here, we know that we are forming 2 alcohols, right? But we're starting off with the alkyne. There's no way that we can go from an alkyne to alcohol, but we do know that we can go from an alkyne to a carboxylic acid, and then from that carboxylic acid we can go into an alcohol. So that's a type of logical reasoning that you have to be able to use when you're attacking these problems. You have to be able to understand that it's a stepwise process. What do I have? How is this different than what I start off with? You see that you had to get rid of this triple bond here. You can get rid of that with either H2PD, but if we do that, there's no way that we can form our alcohols. Therefore, let's just split this up by using O3 CH2Cl2 with zinc and water to then get us this structure, where we would have our Me, and then we would have our carboxylic acid sticking out like this. And then we know now from carboxylic acid we can go to alcohol, doing what? By using LAH. And now we get our final product right there. And kind of similar, here we're starting off with the alkyne, and then we're producing 2 more alcohols. But in this case, what else do we see? Instead of, because we know that if we use O3 CH2Cl2, we're going to produce two molecules that are going to separate in the middle of the alkyne essentially. So we're going to get the same thing we have up here. But what's different with this than this? Here we see that we are removing the carboxylic acid, right? Because we're removing the carboxylic acid, we know that we have to, actually first, let's actually go back to understand why we can't use O3 first. Why can't we use O3 first? Because we're producing a carboxylic acid. Instead, if we produce that carboxylic acid, there's no way that we can add these extra carbons. So that's the main thing you have to understand. You're adding extra carbons, because if you count them out, you started off with 1, 2, 3, 4, 5, 6, 7, and 8. But you ended up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you're adding a lot more carbons than what you started off with. So first, let's see if we can break this down into a different molecule. This is where understanding the different types of reactions comes in place. Because if you understand that O3CH2 will reduce alkynes all the way to carboxylic acids, but only reduce alkenes to aldehydes, then you are able to answer this question. Because now you can use H2 Lindlards to get us an alkene. So then instead of this being triple bonded, it becomes double bonded, right? And then this is going to be cis because it's Lindlar's catalyst, so both of these will be facing down. Now we can use O3CH3 to then get us our aldehydes, like this. And of course, we're going to have two equivalents of the same thing because this side is identical to this side. And now, because we have this structure, we can use Grignard's reagent, which would be CH3, CH2, Mg, to then attack, right? Because Mg is going to hold that positive charge, while this will hold that negative charge. So we're going to have CH3, CH2 minus with the Mg Br plus. And then this is going to attack here, push this electron up there, and then that's going to give us this product that we get. Remember, this is an ethyl group, so that means that now we also have an ethyl with an H like this, and we have that ethyl, which corresponds to that same ethyl we have right there. And then, of course, you need your H3O plus to protonate this and make this into water, into alcohol, I should say. So then you go from this all the way to your final material. So as complex as all of this seems, the more practice you do and the more you go back to understand how each reaction corresponds together, the easier this will become. So it's a matter of just understanding how each reaction, well, first you have to memorize all the reactions. So go back to review and make sure that you have those flashcards, because if you don't memorize all those reactions, then this is going to be pointless. It's going to be very hard for you to understand how to get from this to that if you don't know the reactions. In this case, the mechanisms aren't as important. In some cases, you'll have to know the mechanisms, like with Grignard's reagent, and it just comes down to understanding how do I get from 1 to 2 to 3. They give me this, and then they give me this. What's different between this and this? Or they give me this, and they tell me these are the reagents, what's the product? If they give you that situation, it becomes a matter of just understanding what does each reaction do, which you already understand based on the fact that you already wrote down the mechanisms and you understand how they all correspond together. So hopefully this helps. Another example is here explaining one of the mechanisms of how you go from an alcohol to an alkene, utilizing hydride shifts to give you your major product versus your minor product. It's very important that you guys go through this. The mechanism's already written down, so you can pause and stop here to look at it and understand what's going on. And if you understand this, and you also understand the concepts behind here, then you will do extremely well on your exam. I can't stress enough how important it is to be able to familiarize yourself with all the different reagents and all the different reactions, because if you understand how they all come together and how you can manipulate one to get to another, then it makes this exam a lot simpler.